Welcome to our bridge design masterclass. Today we will be modeling, analyzing, and designing of three spans simply supported bridge. The bridge has a total longitudinal length of 60 meter and a total width of 10.4 meter. So we quickly look at some of the information that has to do with this bridge design. So we have defined the design life of the bridge to be 100 years. So this is the contents of the bridge design. So we have already defined this. So we will be running the computer analysis of the slab traverse, the bridge slab design, which will involve the slab traverse moment, institute, deck institute slab design, deck precast slab design, transition slab design, then parapet and deck slab interface. So we will also have the deck beam design substructure, which will now consist of abutment and the piers. So we will also design the abutment and the piers. So the loading arrangement is going to be the HA plus 45 units of HB load, and it would be in accordance with BS 5400. So we have other code that we are going to use for the design, which will be the 37 stroke 01 load for highway bridges. Okay. Then we have also defined the partial load factor for the ultimate limit state and for serviceability limit state using the BS 5400 part 2. This is the planned geometry of the bridge. So the bridge has a cantilever slab of 1.2, and the main girders are being spaced at 1.6 meter center to center. So the simply supported span for each of the span is 20 meter each. So these are the deck geometry. The overall length of the bridge is 60. The deck span length is 20. Total deck width is 10.4. Then the width of carriageway is 8. Then we have the width of walkway and cape 1.2. Width of each lane is 4 meter. Numbers of girders, talking about the main beams, there are 6 numbers. Then distance between each girder, talking about the main beam, 1.2. Length of overhanging deck 1.2. Height of parapet 1.5. So we have the length for the approach slab to be 5 meter. Then the width for the approach slab is 8 meter. The deck members, thickness of deck institute slab 200, thickness of precast slab. The precast slab the precast slab is 50, so making it 250. The surfacing and overlay, so we use 70 mm. Then parapet wall thickness 200 mm, walkway thickness 350, approach slab thickness 300, then inner cap. Then for the main beam, talking about the main girders, the width is 450, the depth is 200. For the diaphragm beam, we have total width of the width for the diaphragm beam is 450, the depth is 900. Now these are the material properties. So these are the material properties. So this is the traverse geometry of the bridge, which we have defined already. So we have this as the overall width of the bridge. This is the carriage width meter. These are the spacing. So we will move into the modeling of the bridge using robot structural analysis professional. Okay. Okay, so we move to robot software. So when you open the robot software, this is where you can start a new project. Now, the template that we are going to adopt for the bridge design is going to be shell design. So you click on shell design. So the first thing you will do is to save your work. So you come to file, click on file, go to save as. Go to save as. So we are going to save this as 3 span simply supported bridge. Okay, so we save it. Okay, so when once you are done with the saving of your work, you go to tool so that you can do the preliminary setting. Under job preference, you click here. Then you change the material. So you can start with the units, the dimension. So the structure will be in meter, the section millimeter, section property millimeters, then the reinforcement area, everything millimeter. Then the force will be in kilonewton meter. Then you can change this to kilonewton meter. Then others, displacement, you can change this to mm. Then every other thing will remain the same. Then under material, you can modify this material. You can modify this. We are going to use bridges. So let's look for bridges. So you modify the material, change this to steel. So 410 will appear automatically. So you now click on OK. Then under database, we are having the vehicle load. We are using 5400. So click on OK. So we want to define the bridge geometry. So to define bridge geometry, remember that this bridge is three span simply supported bridge. So we are going to model just one span as a representative of others. So you come to the structural axis. So we want to start with the X. Now the X actually represent the traverse section of the bridge. This is the traverse section of the bridge is what the X-axis represents, while the longitudinal represents the Y-axis of it. It represents the Y-axis of it. So this is the longitudinal, this is the traverse. So the traverse is this section that we are cutting. So we want to define this first before we define the longitudinal. So we come back to robots. So the first one there is 0, 0. We just add 0 to it. Then we can change this numbering to ABC. Okay, so we go back. So from here to here is 1.2, 1.2. So we quickly put in 1.2. Numbers of repetition 1. So from that, next one is 1.6. So we go back and check 1.6. We have 1, 2, 3, 4, 5. 1.65. So numbers of repetition here is going to be 5. So we add. Then the next one is 1.2, which is the last one. This is the last one, which is 1.2. So we can add. Okay. So we are done with that. So we go to the longitudinal. The same thing. Same thing. Okay. So in this longitudinal, we are going to have okay, what we will do, let's get the overall longitudinal span, which is 20. It is 20, so we add. Okay, so we come back to this. So when we come back to this, remember that we are going to have a diaphragm beam. We are going to have a diaphragm beam. There will be a diaphragm beam here. This is the diaphragm beam. This is the diaphragm beam. And this also the diaphragm beam. So now while this one is the capping beam. So here what we are going to do, the diaphragm beam is, the width of the diaphragm beam is 450. It's 450. The width of the diaphragm beam is 450. So half of this will give us 225. So we come here. So 0.225. 0.225. So we add. Okay, 0.225. Then after that, we will also have another diaphragm beam on the other side, which we will also subtract. So we will get 20 minus 0.45, 19.55. Yes, 19.55, yes. So we will have 19.55. So we add to this info. So we have 19.55. I think we are done now. We are good to go. So we can now close. Okay, so we have defined the geometry of a beam. This is where we will have the diaphragm beam. This is where we will also have the diaphragm beam. This is where the main girders will be. Remember that the main girders are 6, 1, 2, 3, 4, 5, 6. Okay. While the diaphragm beam will now overhang up to this point. So let's define the boundary of the deck. To define the boundary of the deck, click on geometry, come to object, come to polyline contour. So we click on polyline, use it to define the boundary of the bridge deck. Okay, so we can close. Okay, so we have defined the boundary of the bridge deck. The next thing is for us to place the deck slab. Place the deck slab. To place the deck slab, you come to panel icon. You can get it from here, or you can come to geometry and get the panel icon. Okay, so we under the reinforcement, we click on RC shell, then model remain on shell, then you come here, define the thickness and the name. So this will be deck, and simply put it deck or deck slab, and put deck slab. Then the thickness here is it's going to be 250. Now for global analysis we are going to use 250, but this includes the thickness of the precast slab. So the institute slab thickness and the precast slab thickness. So we use 250 for global analysis. So we define the grade of concrete. We are going to use 3037 grade of concrete. Then you can now act. So you close, then you place it, and you place, you close. So we have been able to define the deck slab now. So let's now start working on the line of application. So we want to define line of application. We want to define the line of application of load. What I mean by line of application of load is what I mean by that. We are going to have a load here. There will be 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 a load. There will be a load. Yes. So we want to define those lines of application for each of these. We should remember that bridge are load sensitive, so we have to be very careful how we apply the load. Okay, so to define line of load application, you come to geometry, come to object again, come to polyline contour. This time around, you're going to use line to define them. So let's define this phase 1. Okay, so we can also define this. Okay, so we have been able to define those two lines. Click on OK. So we go back to this, click on this line number 1. That is line number 1. Okay, so we want to define line for application of parapet load. Line for application of parapet load. We want to define that first. So we come here, click on the line, then come to edit, click on edit, click on move. Then we are defining this line on X direction. This is X direction. This is Y direction. This is Y direction. This is X direction. This is Y positive. This is Y negative. So now I will put 0.2, 0, 0. Then I'll click on copy. So I've defined my line 4. Define my line 4. I will close. Then come to line 3. This is line 3. Then go back to edit. Click on edit. Click on move. So in this case, I'm going to define it on the negative direction of X, which is negative 0.2. Then comma 0, comma, I'll click on execute. Okay, so I've done that. That is my line 5. So I will come back to this. Want to define the overall width of the walkway, which is 1.2. 1.2. So I will go back, click on line 2. It's been highlighted. Come to this, click on this, click on this, click on 1.2, 0, 0, and I'll click on execute. Click on execute, click on OK. Then I'll go back to line 3. This is my line 3. Then click on edit, click on edit, click on edit, click on this. This will be negative 1.2, 0, 0. Click on execute. Okay, so I've been able to define the overall width of the walkway. But let me define the width of the walkway itself. This is kept. This is kept. So I want to define this because we are going to apply load here, the walkway load here. Now, when you subtract 250 from 1,000 to give you 750. So what I will do, I'm going to offset 250 to the left, then 250 to the right. That's what I'm going to do now. So 250 to the left, then 250 to the right, 0.25. So I'll click on this line, which is 6. Then go to edit, click on edit, click on this. Then offset minus 0.25, 0. Okay, I've done that. Then come to 5, no, come to this. Okay, 7, the same thing. This will be positive 2.5, 0, okay. So I have established that. And what again? What again do I need to do? Okay, let me offset the notional length. So to offset the notional length, let's go to this. Let's look at the condition that will help us to know the notional length width. So we have the notional length plus 3.2.9.3 BD37 stroke 10. The notional length shall be taken to be not less than 2.5 meter width. This is the least, meaning that the notional length should not be less than 2.50 width, where the number of notional length exceed 2. Their individual width should not be more than 3.65. So here we have been given the limits. We have been given the limits for the notional length width, that the notional length width should not be less than 2.5 and should not be more than 3.65. It should not be more than 3.65. So the carriageway shall be divided into an integral number of notional lengths having equal width as follows. So carriageway width 5 meter up to and including 7.5. So the notional length shall be what? Shall be 2. So in a situation where you have the carriageway width, this is not the overall width of the road, this is the carriageway width. Carriageway width. Let me show the carriageway width. This is what we mean by carriageway width. This is the carriageway width. This is the carriageway width from this point to this point, while this one is the overall width of the road. So this is where the vehicle load will have effect on. This is where the vehicle load will have effect on. The vehicle load will not have effect here, will not have effect here, but this is the area where the vehicle load will have effect on. So that's what we call the carriageway width. So now, if you have your carriageway width to be up to 5 meter and up to 7.5, the notional length shall be what? 2. So from 5 to 7.5, you have your carriage to be what? To be 2. But if it's above 7.5 up to and including 10.95, your carriage, your numbers of notional length shall be what? Shall be 3. So in our case, our carriageway width is 8. So which fall under this category? It falls under this category because it's above 7.5, though it is not up to 10.95. So as long as it is above 7.5, so it falls on this category. So our national length would be what? Would be 3. Okay. So here we define the national length. So national length width is equal to 8 divided by 3. So we have 2.667. 2.667. So let's apply this on the rough structural analysis. 2.667. So we come back here. So we click on this and go to edit, click on edit, click on move. So this will be 2.6667, 0, 0. So it's going to be just 1, 2. So let me just put here 2. Copy. Okay. So we now have 1, 2, 3. So we have already defined the notional width of the road to be 3. This is where we are going to apply our load. This is where the load is going to be applied. Okay, now that we have defined lines of load application, so let's go to the load definition. Let's begin to define the load for each of the elements. So now, loading on rubber. So I took time to define this so that we will not have problem. So these are the load computation in robot structural analysis professional. So we have 2 categories of load here. We have the dead load and we have the live load. We have the dead load and we have the live load. So this is dead and this one is live load. So we are going to define this respectively. So we go back to robot. So we click on load. Okay, so this is the load dialog box. So under this we have the first one is structural save weights. Structural save weights. So we can denote this by SW, structural save weight. So it is under nature of loads, dead load. So we can add. Okay, we can add. So the next load is superimposed dead load. Superimposed dead load 1, superimposed dead load 2. So these, let's look at those loads that constitute superimposed dead load 1 and superimposed dead load 2. So we have this fall under superimposed dead load 1, this fall under superimposed dead load 1, and this also fall under superimposed dead load 1. So the whole of these three fall under superimposed dead load 1, while this one fall under superimposed dead load 2. So we are going to apply this first. So we have this. So superimposed dead load 1. So we have superimposed superimpose dead load, which is SIDL1. So this will be SIDL1. So we have 2. So this will be surfacing. Superimpose the load 2 is surfacing. 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 Okay. Surfacing. So we move to the next one. The next one is, okay, so we are done with dead load. So we move to live load. We move to live load. We move to live load. Under live load, the first live load we have is HAUDL. 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 Okay, so we HAUDL. So HAUDL. So we add, then followed by HACAL position 1. HACAL position 1. So this is cal live H load cal position 1. Position 1. So this is cal position 1. Cal position 2. So we add, okay, so we move again, pedestrian loading, pedestrian loading, pedestrian loading, pedestrian loading. So we have this as, I use PDL for it. So we add. So we move again to HB45 units, position 1. HB45. HB45 units, position 1. Position 1. So this is HB45 U1. So we add, then we have P2. So P2 is used to investigate the support reaction, while P1 is used to investigate the span moment. Okay, so the next load that we will apply will be HA plus HB loading pairing 1. Now this is for span verification. This one is for span verification. This one is for span verification, while this one is for support verification. Support verification. Okay, so we go back and HA plus HB loading pairing 1. So HA plus HB P1. So we add, then 2, 2. So we add. Okay. So we are done with that. Okay, so now let's go and begin to define these loads as we apply it on the robot. So we come to superimpose dead load 1. So we are starting with that. The save weight, structural save weight is already inbuilt in the robot. So we start with the superimposed dead load 1. So we come to load definition. When you select it here, it will automatically select here. So we come to load definition, we click on surface. We are going to make use of uniform planar load on contour, uniform planar load on contour. So now let's look at, remember that we have already defined that there are 3 loads that make up the superimposed dead load 1, which is the walkway, the curb, the parapet. So we can start with the parapet. The width of the parapet is 0.2. So we have 7.5. 7.5. So here we minus 7.5. So we click on contour definition. So this is where the load will be applied. Will be applied here. Okay, so we have defined that. So we also come to this other side where we can also define it. So we come here. Okay, so that has been defined, but we are not yet done with superimposed dead load 1. The next load that we will consider will be the curb. So let's consider the curb. The curb is 2.1875. 2.1875. So we go back, click on this. Two 2.1875. Let's confirm again. 2.1875. Okay, it's correct. So this is where the cape load will be applied. Click here. Click here. Click here. So we press that. So we come back here. click on contour definition, come to this, click here, click here, click here, click here. Okay, so we are not done yet. The last one is the walkway load, which is 6.5625. 6.5275. So let's confirm that. 6.5, 6.5625, 625, 625, 625. So its line of application will be here, 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 here. So we turn back. Okay. So we click again. Contour definition is the walkway area. Okay, so we are done with the superimposed dead load 1. So we move to 2. We move to 2. Okay, so 2 has to do with surfacing. So the surfacing will be on the entire carriage way. So from here to here. Okay, so what is the magnitude of it? Magnitude is 1.695. 1.695. Click on load definition. Click on surface. Click this one. 1.695. 695. Contour definition. So it's going to be from here to this, 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 and then we return. Click OK. So we are done with that one. So we can close. We move to the next load, which is the HAUDL. The HAUDL is going to be applied on each notional length. So let's look at the calculation for it. The HAUDL, the HAUDL, HAUDL. Okay, so this is the HAUDL, the notional length. So we are using this formula to calculate the HAUDL. This is about 4.149 kilograms per meter. Then we are going to apply it on each notional length. So we have to divide this load by the notional length, which is 2.6675. It will give us this. Then we are not going to apply this. We are going to apply the length factor that will further reduce this, the length factor. So let's go back to this. Let me open to the codes for us to see that load as it is captured in the code. Okay, so for the HA uniform distributed load, this is the loaded length is 20. So you can see that we have 45.1, 45.1, as you can see here, 45.1. Using this formula, we arrive at this. So we divide this load again by the notional width of the road, which further give us 16.931 kilonewton per meter square. Then we have to apply load length factor for this. So the HA loading case, the HA length factor table for 14.0 PD 3701. So let's look at how this length factor is being applied. So we come here, we come to this. Okay, now look at the HA length factors. Now we have the loaded length in meter. So for 0 is less than L is less or equal to 20. The first length factor, beta, is equal to gamma 1. The second length factor, beta 2, is equal to gamma 1. The third length factor, beta 3, is equal to 0.6. So note that gamma 1 is equal to 0.274 BL and cannot exceed 1. So now, whatever that is your BL, well, by the time you multiply with this 0.274, that value should not exceed 1. That value should be less or equal to 1. Should be less or equal to 1. Now, where BL is the notional length width, So we have calculated this. This is 2.667 meter. 2.667 meter. So for first length factor, beta 1 is equal to alpha 1. Then second length factor, beta 2 is equal to alpha 1. So this is how it is being applied here. HAUDL, beta 1 is equal to HAUDL, beta 2. HAUDL times beta 2. Okay, beta 1 is equal to alpha 1, which is 0.274 times 2.667. This is the BL, the notional length width, BL, and we multiply. Remember that the formula is 0.274 BL. So when we multiply that, it gives you 0.73. And for length 2, which has to do with beta 2 is equal to alpha 1, which is the same thing. But for length 3, beta 3 is equal to what? 0.6. 0.6. Okay. 0.6. So here, let's see how it's being applied. So the HAUDL that we are going to put in the robot structural analysis software is going to be 12.37. And we are going to apply this on lane 1 and lane 2. It's going to be applicable on lane 1 and lane 2. 12.37. Lane 1 and lane 2. 12.37. 12.37. So we go back here, load definition, surface, uniform planner, 12.37. So contour definition. So we are going to apply it here, 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 and here. Then. Okay, so we click again, click on contour definition, apply on the second lane. so we are done with that. Then the third lane will be 10.16. The third lane will be 10.16. 10.16. So we go back. Um, 10.16. 10.16. So okay. So we have applied them now. We have applied them. So we are done with HAUDL. So the next load we are going to apply will be HAKL. This is the knife edge load. So the knife edge load for position 1 will be applied on the mid span of the bridge. Will be applied at the mid span of the bridge. So we change this and move to this, the mid span of the bridge. So let's define that mid span. Let's define the mid span of the bridge. So we will simply come to geometry, come to objects, click here, then click on line, the midspan of the bridge is okay. So we have defined that midspan now. We can close. Okay, so let's look at the magnitude of that load. The same thing is also applicable when you are applying the HAKL. The same method, we will multiply by the length factor beta 1, which is equal to alpha 1, and beta 2, which is also equal to what? Beta 2. So the HAKL per notional length is 120. 120 divided by the notional length width, so which will give us 45 kilonewton per meter. So you multiply by the length factor of 0.73, and this will give us 32.9. Now this 32.9 will be applied on lane 1 and 2, but for the lane 3 you multiply this by 0.6, which will give you 27. So we have to apply this on lane 1 and lane 2, then this on lane 3. So let's go. So we come here, come to surface. Now we are going to use linear load 2P, linear load 2P, because it is a knife edge load. It's like a point load from one linear point to the other. So we are making use of this when you are applying this type of load. So you click on linear load 2P. So when you click under Z, you come to minus 32.90. Also click here, minus 32.90. Then you come here, then you click on apply. So the load has been applied. So you come back here, do the same thing, click here, and apply. So it has applied on that one. Then on lane 3, the magnitude will change to 27. 27. So we click here. So this is 27. So we come here. So it's being applied, so we can close now. Okay, so we move to HA position 2, position 2, position 2. Position 2 will be used to investigate the support. So we are going to apply it at 0.05 meter, 0.05 meter. So what we will do is that we will apply it at the edge of the support, then we will move it by 0.05 meter. So let's apply first. Let's apply it at this point. So this, okay, I can apply it at this point. Let me just apply it here. And now add, okay. So I'll come back here again, change this. Thirty-two point nine, 32.9, 32.9. So go back, click here, apply, and close. Okay, so let's move the load from that position to 0.05. So when you come here, you will see that the curl, you see that the first one that we apply, you will see here that the first one we apply, talking about the curl load, was at the midspan, which is 10. The midspan 10, and this one also 10. So here is at 0. So what we will do is we are going to change this. So this will be 0.05. This will be 0.05. 0.05. We come here, we do the same thing. 0.05. 0.05. 0.05. Okay, so we are done with that. Okay, so you can see that the load has been moved from this edge to somewhere here. It has been moved from the edge to somewhere there. Okay, so we are done with that. We are done with that particular load. So the next load that we are going to apply will be the load number 7, which is pedestrian load. The pedestrian load, So let's apply the pedestrian load. So this is the pedestrian load, which is underlying load. Underlying load. This is pedestrian load, underlying load. 5.0. So we are gonna apply it, the pedestrian load. We are gonna apply it from the cape to somewhere to this point. Cape to this point. So we click on load definition. click on surface, click on this, change this to -5, click on contour definition, come to this, put it here, okay. So we do the same thing for the right hand side, click here, okay. So we have finished applying that pedestrian load, so you can close. So the next load that we are going to apply will be the almighty HB 45 units position 1. So this is the most critical load. This is the abnormal load. This is the abnormal load. So this load is actually the axial load. This load is actually the axial load. So let's look at it how it is being analyzed in our design template. So the HB 45 units is equal to 45 times 10, which will give us 45 kilonewton. And this load is divided by 4, which is the 4 wheels that make up an axle. So each wheel will carry 112.5. Each wheel will carry 112.5. Now, this is the code as specify how this load is going to be applied. The abnormal load, the code has taken time to specify how this load is going to be applied. So let me look for that where the arrangement of this load is going to be. Okay, so this is how this load is going to be applied. The load is going to be, this is an axial load. This is an axial load. So 1, 2, 3, 4. It's an axial load. Now the load is going to be applied at from the center to these 4 tires. From center to this 4 tire and to this other one, 3. If we are adopting 6 meters, so it's going to be from here to here is going to be 6 meters. The space is going to be 6 meters. Then we have 1.8. Now, if you are adopting 11, so from here to here is going to be 11 meters. If you are adopting 16, from here to here is going to be 16, and so on and so forth. Now, you said that which dimension produce the most severe effect on the member under consideration. So we are going to consider 6. We are going to consider 6. Now, let's apply this load the way the code has recommended us to apply. So, to apply that load, we are going to use note. We are going to use note to apply the load. So let me turn this so that we can see when this is being applied. So we come to geometry, come to note. So I will pick my first note here, which I already defined. Then I'll click on that note. Then come to load definition. We are going to use nodal force to apply it. So this will be minus 112.5. So let's apply it there. So let's apply it at that point. So we apply it. Let's see the load value. Okay, so that is it. So that is it. So we are going to apply this load. We're going to apply this load at, we are going to space this load at 1 meter, at 1 meter. But what is going to happen is that we will move this load by 0.5 on the x direction. We will move it by 0.5 on the x direction. So to achieve that, why should we move that load by 1.5? Now let's look at what the code has asked us to do. Okay, now depend on judgment of designer. 0.5. Yes. Okay, so we have to adjust this load by 0.5 or 500 mm away from the walkway. So let's demonstrate that right now. So to achieve this, let's close this. Let's come to this geometry. Come to tree. We can. This is H A. Okay. So let me rotate this so that we can see it. So I now come to node. This is node. So I'll click OK. The node is already been highlighted. So I will come to edit. Click on edit. Click on this. I'm going to move this by 0.5. Remember that I'm moving it on the x direction. 0.5, comma. So I will click on move. Okay. So that is move. So I will still copy this by 1 meter by 1 meter using this. This is 1 meter, 1 meter, 1 meter, 1 meter. So I will copy it. I will copy this. So this will be 1, 2, 3. So it's going to be 3 plus the one that we have. Click on this. Click on copy. Okay. So I have copied that now. I've copied that now. So what I want to do right now, this is the center of the bridge. This is a center. The load I've just positioned is somewhere here. So I want to move that load to this point and move it to this point. So let me move this. Let me move this to this point. So we're adopting 6 meters. So half of 6 meters will be 3. Half of 6 meters will be 3. So I will go back, click on this, highlight everything. Then I'm moving it on the negative y-axis. Moving it on the negative y-axis. So I will come to this, click on, come to x is 0, negative 3, comma 0. And I will move it. I will move it on the y-axis. So it has moved from that y-axis. Okay. Then I will copy it 1.8. Copy it 1.8 meter. 1.8 meter. I still go back there, then come here. 1, negative 1, negative 1.8. I will just copy it, negative 1.8. Click on execute. Okay, so that is 1.8. Then I will also copy this by 3 meter again to the right hand side. I'll copy this to the right hand side. So this will be positive 3 meter, comma. I will click on copy. Oh, sorry about that. Sorry about that. That's supposed to be 6 meter. Yes, it's supposed to be 6 meter. Yes, it's supposed to be 6 meter. It's supposed to be 6 meter. Okay. So I will click on copy. Fine. Okay. So I will copy this again by 1.8. 1.8, 0. Copy that by 1.8. Okay. So now I've been able to successfully demonstrate this arrangement. Been able to successfully demonstrate this arrangement. But there is something that we are going to do for us to have the most severe, for us to have the most severe condition, or what we may call maximum bending moment. Maximum bending moment. Now, the maximum bending moment will occur at 1.5 away from the center line of the bridge. 1.5 away from the center line of the bridge, meaning that we are going to move this load 1.5. So this load will now coincide at this position, 1.5, 1.5 away from the center of the bridge. Remember, this is the center of the bridge. So 1.5. So this load will move everything, the whole of this, all this load will move and let it coincide at this point. So that will give us the maximum bending moment. Give us the maximum bending moment. So what we are going to do now is that, okay, let me define the 1.5. Let me define the 1.5. So objects, okay, geometry objects. Let me check the center line. Okay, that is the center line. That's the center line. So I will offset 1.5 to the left. Come here. Okay, so 0 minus 1.5, comma. So I will copy it. Okay, fine. So the load that we are going to move, we are going to move the whole of this load to coincide at this 1.5. So that is what will give us the maximum bending moment, the maximum bending moment. So we go back to the notes. Go back to the notes because we are moving everything. We are moving everything. Okay. So we come to this, click on edit, click on move. So it's going to be on the positive y direction. So 1.5, comma. So we move. We click on move. So you can now see that it has moved that load. So what we have just done, what we have just demonstrated is what we have here. What we have here. So this would now give us, remember that from here to here is 6 meter. This is 30. This is 1.5. This is 1.5. So what we have done is that we have moved the axle load from this point to coincide at this point. it coincide at this point, which still give us the 6 meter, meaning that as this move down here, this equally move up to this, equally move away from this. So this is what will give us the most severe condition and will produce the maximum bending moment. This is where the maximum bending moment will occur. Okay, so this is for position one. This is for position one. This is for position one. So we are going to do the same thing for position two. So we have to do it for position two. So the position two here will be at the support. It's going to be at the support. It's going to be at the support. Um, it's going to be at the support. It's going to be at the support. So we come here, we do the same thing. So we are going to establish our note here. Come to notes. So at this point, okay, so we click. So that is the note. So let's go back to this load at this point. So this is position two. So position two, go to load definition, click on this, add. Okay. So we will also move this. We will move this by 0.5, 0.5, comma 0, comma. So we are going to move it. Okay. So when we are done with that, we will copy it. We are going to copy this. This will be 1, comma 0, comma 0. Copy 3. Execute. Okay. So from here, we go back to geometry so that we can view that. So this is the last one, which is 24. So from 21 to 24, 21 to 24, this, and this, 21 to 24, 21 to 24, 21 to 24. So what we will do here, and we are going to offset 1.8, 6 meter, 1.8 and 1.8. So that will be on the positive side of y-axis. So 0, 1.8, 0. So we copy. Then we change this to 6. Change this to 6. We copy. Then the next one will be 1.8, this fine. So we are done with that now. So we are done with this one now. this is for the HB45 unit position 2. So we are done with this now. So we move to the next one, which is the HA plus HB loading pairing 1 and pairing 2. So this will come under this. Okay, now what we are going to do, we will copy the HB 45 units position 1. We will copy it to this point position. So okay, we will copy it. So let me look at that. Let me look at it. Let me look at it. This is okay. So we are going to copy this. We're going to copy this. We're going to copy this and move it to this. Move it. Move it to this. Move it to that. So we click on this. This is HA. Okay. So this is HA plus HB. This is HA plus HB pairing 1. Now look at, okay. I think, okay. So now we have changed that. So let's apply the other loads. This is HA pairing 1. So let's apply this load. Okay, so let's apply this other load here. Now for HA combined with HB loading case, we have lane 1 and lane 2 shall be straddled by HB loading, which is 112.5. So by the time you look at this, you see that the HB load are straddled on lane 2. Lane 1 and lane 2 shall be straddled by HB loading. So you see that it has straddled on lane 2. So part of the HB load is on lane 2. So now we are going to apply the HA UDL times beta 3 at the third lane. So now that this H112.5, which is the HB loading, is straddled on lane 2. So we are going to apply this on lane 3. So we are going to apply this now. We're going to apply this. So let's go to load. Let me go to load definition. This. So this will become 10.16. So let me confirm. 10.16. Yes, I'm correct. 10.16. So I'm gonna apply it. Okay. Contour definition. So we click it here. Okay. So this is for position 1, for parent 1. This will give us the maximum bending moment. This will give us the maximum bending moment. Remember that this load has been adjusted by 1.5 from the center line. So this will give us the maximum bending moment. So we have to also do the same for parent 2. So we come here, parent 2. So let me close it. So parent 2, we are going to copy the HB45 unit position 2 to get that done. Yes, that is what we are going to do. So let me look at it. This is position 1, this is position 2. I will copy this one, copy this, then come to parent 2, place it here, paste, then come here, change this to parent 2. Perfect. So that is perfect. That is perfect. So we have this one. We have this. We come to this one. We have it. Okay. We come to this. Fine. We come to this one. We have it. Fine. Perfect. Then let's move to this. Okay. This is wonderful. This is wonderful. So we are going to apply the same for parent 2. Okay. For parent 2. So we click on load definition, click on this, the same load. This one is used for support verification. One is used for support verification. Okay, so fine. So we are done with that now. So we can close. So let's look at the different loading now. Let's look at the different loading now. So we have the step weights, we have the impulse, we have the surfacing, we have the HUDL, we have the curl for position 1, we have for position 2, we have the pedestrian load, we have the H45 units position 1, we have for position 2, we have this one for parent 1, then we have for the support. Okay, that is parent 2. So we have successfully defined all the loads. So the next thing that we will do in our next module is for us to now define the B and now run the analysis where we can extract the bending moment and the shear force. Okay, so thank you very much. See you in our next